What's happening, folks? Geologist Philip Prince got you looking out over what is said to be America's most beautiful national park. If you cannot identify it just by looking at it in Google Earth, I would be very impressed if you could. It's Glacier National Park. And one of the Google Earth clues that might point you in that direction, if you were somebody that was pretty into geology, or maybe if you'd spent time along this lake here, McDonald Lake, that's the pink color that you can see in the exposed rock that is outcropping on these really rugged mountains here. That pink rock layer and others like it are sandwiched in between rock layers that are gray or kind of blue or a little bit green. When they erode and pieces of them get washed down to the lake, it ends up making these really colorful pebbles that the shorelines of McDonald Lake are so famous for. Now, Glacier is a standout in terms of national park scenery, largely because of the geologic structure that's present here. It has also been carved up by glaciers in the past. The actual glaciers today are less and less a part of the park because they're melting quite quickly. But absolutely, the geologic backdrop here is a really big part of what makes this place so distinct in terms of its scenery and just kind of the feel of being there. You never know what you're going to get with Google Earth imagery. Sometimes you get a little bit of color distortion or exaggeration like you're seeing here, but absolutely the rock there is colored. It is very dramatically layered. Everything that you're seeing here is sedimentary rock that was deposited in water, buried under a tremendous amount of additional sediment, and then actually pushed up and exposed by erosion. But despite all of that history, a lot of the layering you see here is very intact. It's not all wrinkled up like you see in so many mountainous areas in the world where there has been squeezing of the rock mass in Earth's crust. And just looking at it on Google Earth here, you can track these layers very beautifully along the sides of the mountains, and you can even see a little bit of that red or maroon color laying up against the gray or sort of the gray green color there. Beauty of Google Earth, of course, in a place like this is it allows you to kind of fly around and explore things in a way that would be very difficult from the ground. Even if you were able to climb to the top of this mountain, for example, it wouldn't be possible to get the same view that we're getting right now. And it's really this layered structure and that very gentle tilt or dip of the layering that's kind of the essence of the video here, because that's what really sets Glacier apart in terms of the geologic backdrop. So many national parks are really defined by the natural features, which are fundamentally, in most cases, the geologic features that establish the landscape within them. And Glacier is no exception. It actually has a fair amount in common, believe it or not, with the Great Smoky Mountains National Park, and I'll touch more on that at the end of the video. But when you go to a place like Glacier, you're going to see elements of geology and of geologic history and process that are sometimes kind of tough to tough to pull all together when you're on the ground here. And Google Earth is very nice in that it will actually allow you to get on the ground and get a sense for what you might see if you were on the Going to the Sun Road here in Glacier. A lot of cars, first and foremost, but that layered sedimentary rock structure there is very clearly visible, of course, if you're driving there, and also from just the Google Earth Street View here. It goes up above you, all around you, in all directions. Hopefully, the screen is keeping up here, but actually, as we look off into the distance here, you can see that layered structure brilliantly up on this mountain peak here. So this mountain, like everything around it, has actually been carved out of a much thicker package of rock. The mountain as you see it today is very much a product of erosion, and the rocks that it's made of have had sort of an interesting history from being transported as sediment, deposited underwater, buried under a bunch more sediment, and then being kind of pushed up or squeezed up and eroded to sculpt out the features that you see today. So, bearing in mind that geologic structure and the rock types here are sort of a defining feature of this national park. What in terms of big picture geology, what actually makes it look like it does? And what I mean by that, you really need to zoom out here, get our view tilted again. What I mean by that is it's got a really sharp western boundary. It's got a really sharp eastern boundary. In fact, it goes out to just sort of plains and prairie here in Alberta, Canada. And between those sharp boundaries, you got this really rugged topography that has thousands of feet of sedimentary rock layers that that really aren't wrinkled and folded. In fact, most of them that you look at would not tilt more than 15 degrees or something like that. So what what are you looking at in terms of geologic process? In particular, how does collisional tectonics, sort of squeezing the Earth's crust, produce an arrangement like this? One of my favorite structural provinces here, this kind of outer edge of the Rocky Mountains, and specifically ones like this, where you have big packages of sedimentary rock that are being pushed along big faults, which we call thrust faults. This lends itself very well to a Microsoft Paint diagram. So hang on just a minute. We'll get this thing sketched out. And hopefully, when we come back, when you see this arrangement here and you think about those very gently tilted layers, it's going to make a lot more sense, and it will kind of put the uniqueness of this park into context. So hang on just a minute. Okay, so what's up with geology here in Glacier Park, and what is this 14,000 foot secret? Really cool diagram to lay out here. One of my favorites, because of the way that structural geology impacts this really awesome landscape. So starting off the block diagram here, got mountains, some bigger mountains. That's going to be the kind of the heart of Glacier there. And right away here, actually, we can go ahead and draw the most important line in the diagram. That's what's actually going to be the bottom boundary of this big, thick slab of rocks. It happens to be about 14,000 feet, geologists estimate, in the area. And that is what's going to be really defining why Glacier looks like it does. And we're also going to need to lay out a few more geologic zones within this diagram, and they're all going to be related to how the various sedimentary layers have been sort of wrinkled and stacked up on top of themselves underneath this landscape. Doing pretty well here. Let's see, we'll get that going on. We got to have some crazy stuff happening on this side. Glacier, of course, is sort of like abruptly bounded on either side by flatter terrain. You got to be sure here that your the diagram expresses that, because ultimately those boundaries are related to geologic features. So you got to be sure that everything's in the right place here. So you can get some more mountains going over here down to that flat land, no problem. And at this point, we should be able to start kind of drawing out some of our topography. Obviously going to have like these incredible gorges here stretching out towards the flat land on the east side. Some of these mountain ridges, are really steep and almost pinnacle-like, sticking up above everything else. Got really steep gorges here on the west side of the park. Okay. Right here in the middle, I have this funny little, it's almost like an oval shaped kind of landform that I'm going to talk about later in the video. And we'll just kind of like try to finish up from there. Complex topography, really anywhere you go, but no matter where you're looking at it, most of what you're going to see is those rock layers that are not they're not terribly steeply tilted. So let's color this thing in here. Pink layer, an important one. This is the belt, BELT supergroup. This is the formation that has those really brightly colored rocks that end up as pebbles in McDonald Lake. Big, huge, thick sequence of sedimentary rocks, and it's actually been pushed up and over, sort of stacked on top of younger sedimentary layers. color one set of those there with that kind of blue gray. And the colors I'm using here are ones that you see fairly regularly used in diagrams of this area. There's a very famous one that I think is actually it's been around a while. It's from the late 70s, if I'm not mistaken. It was done, I think, back when they were interested in oil and gas in this part of the world. But of course, the park today is all about just the natural beauty. So we've got all these interesting kind of geologic parts down there in the subsurface. I'm gonna give myself a little bit more topography here to ultimately enhance a little bit later on in the sketch there. We're doing pretty well here. We'll have some rough topography coming down into this basin as well. Okay, and this flat area that I keep referencing, this is the Kishenine. I think that's how they pronounce it, Kishenine Basin. Lake McDonald that has all the pretty rocks in it sort of comes like out of a valley down there into this Kishenine Basin. The Kishenine Basin has really different stuff underneath it, and what you're looking at here is stacking the belt up on top of the younger layers to produce this, and then stretching it back apart so some of those stack layers collapse back down. You see them down here under the basin, and that actually chops chops the big slab of belt there off on either side and produces those abrupt boundaries on either side of Glacier Park there, or at least the higher topography in Glacier Park. And we'll, as a final touch, draw these sort of form lines here that would show how the layers are bent. And you can see here they've got just this faint kind of kind of like trough-like U-shaped bend to them. They would have structure down here as well going underneath the Kishenine Basin, and then of course where you can see those rocks outcropping again back in the direction of like Kalispell. This overall structure is what gives you the layout of the park there. And the final thing that we need to throw in here, we need some representation of some of those different colored layers in the belt that give you that beautiful kind of striped appearance. The reason that they're pink and green has to do with the conditions in the water where the sediments were deposited. If there was availability of oxygen, it oxidized the iron to that kind of pink or red or maroon color. If there wasn't a bunch of oxygen available, you end up with that kind of gray or green when the iron is still reduced. So kind of a cool story behind the colors there. And when you see those colors kind of running out across the landscape, that's because that's where they're outcropping on the surface, right? So those stripes that you see within the glacier landscape are actually sort of like the geologic framework exposed at the land surface. So when someone like me that spends a lot of time with this type of geology looks at that landscape, they're thinking about how are the rock layers tilted, what kind of layers are present, and it's actually possible to kind of read some of the structure out of the whole area just by looking at it in sort of a big picture way like that. So it's a really amazing part of the world. And the big structure down here, this big thrust fault is called the Lewis thrust fault. Certain areas of it here, kind of right along the edge, you can see mountains kind of like the one drawn right here. Sometimes you see even more extreme examples where just the very last bit of the top of the thrust fault is present, and you can end up with almost like a what's almost kind of like an orphan mountain there sticking out right at the edge, and it's just the very last shred of that thrust sheet that's yet to be eroded away. So it's a really remarkable place to think about the type of geologic movement that creates landscapes like this. And if you tried to sort of sum the whole thing up here, I guess, kind of as quickly as possible, take a sequence of rocks like this, gonna shorten it quite a bit. So we're gonna like kind of stack it up of itself like that. So you got kind of a different setup at this point. The thickening of layers associated with that. And then you can pull it back apart. Pull it back apart here. You're going to kind of drop a block down like that, and that's going to give you a place to form that Pictionine Basin. And while all of this is going on, there's plenty of erosion going on. So the landscape is constantly changing, but get something like that, and that's the overall essence of like stacking it on top of itself, pulling it back apart, and thus leaving behind this huge, what, 2 and 4/5 mile thick slab of rocks that used to be quite deep in the earth. Now they've been pushed up onto younger layers, and they're kind of cut off on either side by these faults. So you get just this island of really incredible geology. It gets carved up by glaciers, and you got a park like you see at Glacier today, right? So we'll take it back to Google Earth now and take a little bit more of a closer look at some of the things you can see there in the park, particularly like this little oval guy right there in the middle. So hang on just a minute. Okay, so that's sort of the long and short of Glacier's tectonic evolution and why the rocks there are set up like they are today. Got a fault boundary on the east side, a fault boundary on the west side. Here on the east side, that's from rocks being pushed in at a pretty low angle. Over here on the west side, they've been pulled back apart, sort of collapsed downward. That produced this basin. Today, everything is eroding here, but that fault that chopped off the west part there, that steep, what we call a normal fault related to pulling the rocks of the crust apart, it's made this really abrupt boundary that kind of frames up this incredibly rough topography that exposes those really remarkable pink and green rocks of the belt supergroup and that very gentle kind of structure there. So a really amazing area. The structure is distinct from what you see to the south here in the Sawtooth Range. This is another place where sedimentary layers have been kind of thrust and stacked on top of one another, but the pattern there is different. You don't have this big structure of belt sitting on top of that right here. So it produces a different ridge pattern. And fundamentally, the topography there is it's just not the same as what you see up here in Glacier. And the difference between the two is absolutely a result of structural geology. So if you find yourself here trying to check out Glacier through Google Earth, you know, anywhere you go, you will see evidence of these fundamental elements of the place, which are, excuse me, the nearly flat lying or very gently tilting sedimentary layers, that maroon kind of pink and green color there. And if you take yourself right here to sort of the middle of the structure, you can actually see kind of the core or the axis of that gentle fold, and we can actually draw that in here. Put some colors on there. You can see that the layers here are actually producing that kind of gentle trough shaped fold there. If you zoom out further, you can actually differentiate that little area that we just looked at from everything around it. And the overall idea here from a view like this, you got layers going like that, right through that axis, and then out the other side. So really a unique mountain landscape in the sense that what's highlighted by yellow there, this big sort of slab of sedimentary rock of the belt supergroup that's been pushed in on the Lewis thrust, it's very much intact. It's not broken up internally. It's not wrinkled and folded, and that gives you the really unique kind of background structural geology and the landscape that has resulted from that geology being carved up by glaciers and now rivers over time. You bring yourself down south here and take a look at what's called the Sawtooth Range. you can see that up here in Glacier, just the grain of the land, the color of the rocks exposed, it's all quite different. The rocks here that are folded up to make the sawteeth. This is another place where there's kind of shingled slabs of sedimentary rock. Those are down underneath the big slab of the belt supergroup there. There's not a big slab of belt rocks on top of this, and as a result, the landscape looks very different, and you don't have that same character of topography that makes Glacier up here so special. Now, there's sort of a ruggedness and a beauty, and actually like a structural complexity down here in the Sawteeth that's really cool in its own right. It's just a different type of a landscape, and that, of course, is why the one up here in Glacier has caught people's attention for so long. So I said earlier, like it's actually got a lot in common with another national park. In fact, what is the most visited national park in the U.S., and that's the Great Smoky Mountains. So just to kind of give a thought on that, we'll fly over there real quick with Google Earth, and I know this will take the screen a minute to catch up here, but both of these parks really owe their existence, which is rooted in the landscapes, to structural geology. And in fact, the idea of the belt supergroup sitting up there in that kind of big slab on now on top of the ground there and making those kind of flat lying outcrops that invites comparison to what you have at the Smokies. Now, in the case of Glacier, you would have the big belt supergroup outcrop area, and then you go out to kind of the prairie there in Alberta where shale type bedrock is exposed. It just doesn't make much topography, but it's that fault boundary where one type of rock has been pushed up over another one, and then erosion has occurred that makes that break in the landscape, and it gives you really, really huge mountains and then a much flatter landscape next to it. That's actually what you have here it's what you have here in the Smokies as well. And if you orient yourself and look north along the Appalachians. Now, in this case, the pushing is like this. In the case of Glacier, it was left to right on the screen. In this case, it's right to left. But much like over there in Glacier, there's actually a number of big fault boundaries that run through here. The overall idea being that rocks here pushed in that direction, and you got a bunch of wrinkled and folded layers that are down underneath them here, and they're actually poking out here in the surface of the valley and ridge. So it's the same kind of older, pushed up over younger relationship. It's a geologic boundary that's defined by a big thrust fault, and the rocks on top of the thrust fault are part of a big package of sedimentary layers. It's the Great Smoky group here. It's sort of like the belt super group out in Glacier. They've been pushed into place, and erosion has etched them out. They're so different from the rocks next to them, they hold up really massive topography. The background layers are covered in trees here. The kind of grain of the landscape's different. It's not been glaciated, but a big part of being in the Smokies is standing up on top of some of these high peaks here and looking out over the lower topography around you. And that is sort of the same kind of experience, that you get out in Glacier, and both of them are the result ultimately of big thrust fault systems. So kind of a cool comparison. I guess you could say that like big thrust faults and erosion make really nice places for national parks. And the Smokies here, this part of Appalachia, again, that probably warrants its own video. But absolutely, the sketch that'll come out of that one will end up looking quite a bit like the one that you just saw here for Glacier. One of the big differences is in this case, you're not going to see that evidence of pulling back apart. But in terms of the idea of pushing something up and over younger rocks and eroding it, absolutely, that is the essence of what makes the Smokies the Smokies. And in fact, it has produced in the view that you're seeing here from Gatlinburg up to the top of Mount LeConte. It's the largest topographic relief anywhere on the East Coast, and it's fundamentally just a result of thrust faulting followed by a lot of erosion. So started in Glacier, ended up back in the Appalachians. I guess it's kind of hard for me to leave sometime. But Smokey's here. We'll get their own video, and I hope you check it out when I finally get it put together.